Hello again. So in this session, we want to use the Reynolds transport theorem that we learned in the previous session and drive some conservation laws for fluids. So instead of setting B, instead of using B system here, we set some fluid parameters and then derive the conservation laws. For instance, we first, as you remember, B equals to m times b, right? So first we set capped small b to 1. This will give us conservation of mass or continuity. And then we set b to v instead of b, we set it to v, and this will give us the conservation of momentum. Okay, this equation. So we want to drive this equation, these conservation laws, using this transport theorem. Okay, and the first one I want to drive is conservation of mass or continuity. Okay, so again, let's set b equals to m and or mass to drive the continuity equation in the integral form. So just in a very brief explanation or brief intuition of the continuity equation states just this brief sentence and this brief concept that the time rate of change of the system mass equals to 0. Okay, what does this mean? This means if you have a system, the time rate of change of this mass in that system is 0. Okay, and so the system is what? The system is, we define it as a collection of unchanged contents. Okay, so this is the kind of the conservation of mass. And so what does this mean if you want to describe and represent this statement in terms of mathematical symbols? This means that the rate of the change, so the derivative of the rate of the change of the mass system, so it's going to be m of system with respect to time, because this is the time rate of that, equals to 0. Right? So this is the kind of continuity of mass equation. And we know that the mass of the system can be represented as the integral of the total mass of the system can be represented of all small elements, the mass of all the small elements, or dm's, integrated over the whole system. And dm equals to, I can write dm as rho times dv, right? Density times, if the density is constant, I can write it as rho. I can take the rho out of that, but for now I just write it inside, so it's going to be rho times dv, right? V is volume here. So this is the total mass of the system that is defined here. And now using this, I want to write the Reynolds transport theorem. So to write this total derivative, which we have here, in terms of this partial derivative, and also this flux here on the right hand side, the flux terms, surface flux terms. Okay, so write Reynolds transport theorem with B equals to mass and small b equals to 1. Okay? So instead of dB system, so dB system is gonna be just the mass of the system. Okay? So I just write it down, dm system over dt equals to, so instead of d mass of system, I just write this down here, this definition. It's gonna be d over dt of the integral of system over the whole system of rho dv equals to the sum of these two terms, partial over partial t of rho b dv, and b here is 1, right? Small b is 1, so I just set this to 1. This is the kind of problem statement that we started with, and this b is also 1, so I just set this to 1 as well, and then just rewrite these terms. So just for you to see the similarity, I want to change this a little bit. So maybe make this way so you can see the how I write this down. So it's going to be d over dt of that rho over, it's going to be partial over partial t of integral over cv of rho dv plus the integral over the control surface of rho v dot n dA over the surface. Okay, so these are just these terms, right? These are just these terms from the Reynolds transport theorem that I wrote them down. Okay, so what do these mean? Let's see, what do these mean? So the first term on the left hand side, or this term, means this is the time rate of change of the mass of the system. This is the time rate of change of the mass of the system equals to what? Then the other term is time rate of change of the contents of the control volume. So a fixed control volume in space, you see what is the time rate of change of the contents inside that control volume, plus net rate of flow of mass through the control surface. Okay, so what this means, this equation means that the time rate of change of the mass of the total system equals to the time rate of, so if you have like again, you have any kind of control volume here. Let's say a fixed control volume in space, something like maybe this. Okay. So the total change of the mass of the system equals to the time rate. The total time rate of change of the mass of the system equals to the time rate of change of the contents of this CV, whatever it is inside, what it is changed, whether it's added or kind of subtracted or kind of reduced from this system, plus the net rate of the flow, of mass. So how much it is coming in, how much it goes out. So the net rate of that through the control surfaces. So these are the control surfaces, right? So this will be the total change, the total time rate of the change of the mass of the system. Okay. This is what these equations and these integral mean. So let's investigate this further. For example, for a steady flow and also then for an unsteady flow, and look at the implications of this formula and then get the continuity equation. Okay. So say here we have a fixed control volume in space. Okay, I want to plot a control volume in space. Let me plot this. So say we have a control volume like this. Okay, and I want to plot this in two times. So one at time t. So this is time t. And the other one is at time t plus delta t. Okay? So these are both, again, let me show them with another color, maybe with this. These are both fixed control volume or CV. Okay. So now I want to show the system. So say we have a system of fluid at time t. The system is here. The system of fluid that we are considering is here. So this has a velocity v1 here and a velocity v2 here. And so this is system. And then at time t plus delta t, it goes further to the right, so it becomes something like this. Again, this is the system, our system. So this is the system at two times, one at time t and one is at time t plus delta t. And for a steady flow, let's see what would be the implications for this continuity equation. So for a steady flow, the time rate of change of the mass of the contents of the fluid of the fixed CV is 0. So the time rate of change of the mass of the contents of the fluid CV is 0. This is a definition of a steady flow. This is just a definition. So what does this mean? This means that the partial over partial t of the integral over the CV of rho dv equals to 0. This is just this term. Okay, so this is the definition of a steady flow. Okay. So just to make a note, this is not necessarily true. This is not true for unsteady flow. So for unsteady flows, this the content of the time rate of the content of the fluid CV is not necessarily 0. Okay, so let me now describe this again using this kind of figure that we have here. So what does this mean? This kind of continuity equation. This continuity equation means that the time rate of change of the mass of the system, which is this, let's say, green thing here. So let me color it here. If you imagine or consider a system of fluid, this says that the time rate of change of the mass of the system equals to the time rate of change of the mass of the control volume. How much of the mass is changed within this control volume that I have shown here. So let me show it again. So this control volume, how much of the mass is changed here, which would be this part, right? How much is it changed here? Plus, what is the net rate of the flow of mass through the control surfaces? So how much of it is it coming in? So for example, this is coming into this from this control surfaces. So we also have to add that into the net rate of change of the mass of the system, okay? So this is how you can view the difference between a mass and the system and the control volume. So what is it? I just want to note, what is the difference between a control volume, the main difference, and a system? So a control volume is something that is fixed in space, for example, in laboratory. Okay, so for example, you can set up an experiment and then, for example, open channel flows, right? You have an open channel. Okay. And so in this open channel flow, you have, you fix your devices somewhere, right? The device that you are calculating, for example, here. So that fixed space in the laboratory would be your control volume, right? So this will be your control volume, okay? And so your system or fluid goes through this kind of fixed control volume. You measure the changes inside this control volume with some equipment that you have, and then you also measure the kind of the mass that is going through these control surfaces, right? So you also have to consider that. So you also consider the masses that are going through these control surfaces. And then using these two, if you sum these two together, you will get the total time rate of change of the mass of the system, the mass of the fluid system that is here, okay? So this is how just the difference between system and control volume and what do these terms mean, okay? So now this was in terms of physics and the intuition, and now in terms of the mathematics, so we define the steady flow as a flow where this term, the time rate of change of the system, of the change of the contents of the control volume is 0. This is a steady flow. That means the flow is steady in time, so it shouldn't have any time dependency, right? So this term should be 0 because partial over t should be means that whether the system is changing in time or not. And so if you have a steady flow, the steadiness means that the partial over partial t of anything should be 0. So that's for a steady system where it's not changing in time. So therefore this term, the first term, should be 0. Okay? And so we only have this term for a steady flow, okay? And so the general continuity equation, what we call it is as follows. So the continuity equation we know because of conservation of mass, the total change of the system. So if, for example, you are running an experiment here, so you supply some water, say from here, and then you take the water back and then recirculate it, right, to this open channel flow, okay? So the total change of the mass of the system in this kind of system should stay constant. The total mass of the system should stay constant, so the time rate of change of the total mass of the system is 0, right? Why? Because, again, your total mass of the system is constant. This is a conservation of mass, right? It's conserved. It's not like, it means that the mass is not the total mass into the system. In the system of fluid that you are considering is not going to increase suddenly or decrease suddenly, right? And so the total mass of the system is constant, so this is the conservation of mass. And so because this is constant, we can say that the total mass rate of the system should be 0, right? The derivative of a constant is always 0. So I can write this down. dm of system, this is the conservation of mass, over dt is 0. Okay, so this is the left-hand side of this equation. So when the left-hand side of this equation is 0, so the right-hand side should also become 0. So this is the left-hand side, or LHS, which is 0. And thus, the continuity equation is as follows. This is just the sum of those two terms, partial over partial t, over the control volume of rho dv plus the integral over the control surface of rho v dot n dA is 0. Okay, so this is the continuity equation, the general form of the continuity equation in three dimensions. Of course, it's much simpler for a one dimension or two dimension, but this is the general form for a three-dimensional flow. And also for a steady flow, this becomes 0. So we are only left with this term for a steady flow, okay? When we write the continuity equation. And just to give you an idea again, what does this mean? I'm gonna show this further. So this is an important equation. I just wanna emphasize on that. So just to remind you, what does this mean? I wanna drive that mass flow rate that we learned before about continuity equation in the previous chapter, okay? So this is the integral of rho v dot n dA. If you remember, we had it here, right? So this is what? This is just, this integral is just p dot out minus p dot in, right? You see it here. Let me show it with this color. Just look at these two. This integral is b dot out minus b dot in, and here we have said capital B to equal to m, right? And b to 1. Okay. So in essence, this integral equals to m dot out. So instead of b, I should write m. So it's going to be m dot out minus m dot in. Okay. So I just want to write this down. So let me clean this. Okay, so I just want to write that down again. So instead of this, I'm just going to write this is equals to, because this is over the control surfaces. So this equals to the whole mass flow rate that goes out of the domain minus the total, the sum of the mass that comes into the domain, mass flow rate that comes into the domain. So this again means the net flow rate through the control surface. Okay. And what is the mass flow rate? If you remember from last chapter, mass flow rate is m dot equals to, if you remember, we can write this m dot as rho, instead of m, write rho v dot. And because rho is constant, I can assume rho is constant and take that out. So it's going to be rho v dot, right? Rho v dot. And say for a two-dimensional flow where A also is constant, say we have an open channel flow, right? A simple case, or a pipe flow, say a pipe flow. We have a pipe here. So this A is constant. So in this flow, A is constant. So instead of V, I can write that as A times, say, this say if you have this x here, something, this is like x, okay? So you have ax dot, and because a is constant, I can take a out, so it's going to be rho dA, rho a, x dot, and instead of x dot, I will write dx over dt, okay? And what does this equal to? This dx over dt, if you have a fluid here, is what? Is velocity, right? This is velocity. So I can write this as rho a v. Okay, so I can write this as rho AV, which equals to, so AV is discharge, is what we call discharge, and we defined it before, if you remember. So M dot is just rho Q, or rho AV, right? So this means that this term is gonna be, for example, if you have a V1 here, if you have a V, say for a two-dimensional case, let me write this down, for a two-dimensional case, if your V is, you have V2 here, and then you have for one dimension, this is one dimensional case, it's gonna be this term, or this integral, is gonna be rho a v2, which is what is going out, right, minus what is coming in to this from this control surface, right? This is, if you're, this is your control volume, okay? It's gonna be rho a v1. This is simply this, right? This just simply represents this. Okay. So another note I want to make is, based on this this term, we can also define a average velocity. So let me define that, especially, for example, for like some pipe flows, the velocity is not necessarily constant, right? It can change across the cross section, okay? So we can define an average velocity to write this down. So average velocity. So say you have a here, so instead of these constant velocities that I have written, so you might have a velocity profile that looks like this. Right, if this is, for example, the vertical direction, so the velocity profile can look like this. So then we can define an average velocity, which would be the average of these velocities, something like somewhere like here would be the average of that. So this is V, and the average velocity, we call that V bar. Okay, so if you take the integral over the A, over the surface of rho V bar dot N dot N dA, we can define the average velocity as the velocity that equals to this whole integral. So it's going to be rho V bar A, okay, and v bar is defined, the average velocity is defined as the integral over that area or control surface rho v dot n dA over rho a. And if it is constant, if rho is constant, then this is going to be just cancel out. So you are going to have just integral of a of v dot n dA over a, right? So this would be the definition of the average velocity. And so here you can use an average velocity here. So if you don't have a linear profile, so say it is the average velocity here is v bar 2 and the average velocity here is v bar 1, then again you can write the same thing here. It's going to be rho v bar 2 a minus rho v bar 1 a. Okay, so this is how you can write this term in this equation. Okay. So now let me solve one example of this so you get more familiar with it, how you can write it down. So example. So example. Calculate the average air velocity for this velocity problem at section 1, okay, which is here. So here, say we have a pipe flow and the air is flowing through this pipe. And now what I want to do is I want to calculate the average velocity of this velocity profile here. At section 1. Okay, so this is the definition of that. So let's do it. Flow is steady. What does that mean? That means that this term is going to be 0. And D1 is constant. D1 equals to D2 equals to 4 inch. This is a 4-inch pipe. The pressure at section 1 is 100 psi. The other one is at section 2 is 18.4 psi. These are given. T2 is 553 and T1 is 540, and the V bar, which is the average velocity at section 2, is given as 1000 foot per second. Okay, so the answer, let's look at the answer, how we can solve this. So first of all, we have to select the control volume here. So this control volume was not given and I just added it here. So you select the control volume, which is the fixed control volume in space. So I select this control volume. This is the first thing you do in this type of fluid problems. So you select the control volume that contains the information of both given data. So this control volume should have section 1 data and also section 2 data. So that's why I draw it from here to here. Okay. Then we write the continuity equation for the blue CV, control volume. So let's write that. I have this continuity equation. Let me just put it here. So this is the continuity equation, okay? And because the flow is steady, this is given here. So this term is gonna be 0. Steady flow, because of steady flow. And so I'm only left with the other term. So the other term is the integral over the control surface of this control volume. So let me put it a little bit higher. Of rho v dot n dA, which equals to rho 2, the control surface. So how much is it going out of the control surface? So from these two surfaces, no flow goes out or in, right? This is a pipe flow. So there is no flow that goes out or into this surface, right? The same thing for this surface. Nothing goes in and out of that. And only in these two surfaces, so in these two surfaces, in this surface the flow comes in, we have an inflow, and in this surface we have an outflow, right? So again, we have to subtract the inflow from the outflow, because this is going to be positive, right? Because the n is always, as we define the normal vector, it's always out of the flow. This is how we define the normal vector. So the normal vector, let's say here is this way, and the normal vector for this control volume here is this way, is always defined outward. So n dot v here is positive and n dot v here is negative, right? So we have to, this is another way to double check that you are writing this correctly. So outflow is rho 2 v bar 2 a2, which is at this section, minus the inflow, which is going to be rho 1 v bar 1 a1. Okay, so this equals to 0. And since a1 equals to a2, I can write v bar 1 is gonna be, and v bar 1 is what we want, right? The average velocity at section 1, we don't know that. And we want to find it. So v bar 1 is gonna be rho 2 over rho 1 times v bar 2. Okay? And so I know v bar 2 is given, but I don't know the difference between the density of the air here and here. So rho 2, I know the pressure and also temperature. And what does this remind you when you have pressure and temperature in a gas? Think about it a little bit. Yeah. It should remind us of ideal gas law, right? So ideal gas equation of state is rho equals to P over RT. Okay? So V bar 1 equals to, instead of rho, I just write P over RT. So it's going to be P2 over RT2 over P1 over RT1. So these times V bar 2. And so these r's are going to cancel out. So I only will have P2 times T1 over times V bar 2 over P1 times T2, right? This is what I'm gonna have. Which equals to 18.4. I just now have everything. I have P and T, 18.4 PSI. $540 and 1,000, which is V bar 2 foot per second. You should be careful about the units, over 100 PSI times 453, which is the temperature, sorry, here, right? This is T2. And if you calculate this, this is going to give us 219 foot per second. Okay. So this is how we could use the continuity equation to solve this kind of problems. So let me now just briefly review what we learned today. So in the next lecture, I'm gonna introduce, use the, instead of here we used B equals to M, right? So we set B, small b to 1. So in the next lecture, I'm gonna set B to V instead of 1. So big B is gonna be MV, okay? And using this, I'm gonna drive the conservation of linear momentum equation, okay? And once we drive the conservation of linear momentum, we can solve a lot of problems in fluid systems by choosing the right control volume to be able, and we will be able to solve the forces that are acting on kind of fluid systems for flows that are actually moving, not like the hydrostatic forces for flows that are at rest. Okay, and then after that we will solve many examples, at least 2 to 3 examples for this section. And after that we will do another, we will study another conservation law in fluids, which is the energy conservation law. And we will drive the Bernoulli again using that energy conservation law. And this will be the end of this chapter, okay? So, let me briefly overview what we learned today. So we started with conservation of mass. So in short, the conservation of mass states that the time rate of change of the system mass, the total system mass, is 0. And system is a collection of unchanged contents, right? For example, this here that I've shown. So the total change of this system is going to be the total change, the time rate of change of the system mass is going to be 0. And as I said, that is because your mass, the mass of the system is constant because it's unchanged contents, right? So if you take the derivative of that with respect to time, that should be 0, right? So this is what, in short, the conservation of mass kind of states. So in terms of mathematical symbols, this means that dm of system, the total derivative of mass of the system with respect to time is 0. And this is the definition of mass, which we can write it in terms of integral of all the small elements. And then we take this and write the Reynolds transport theorem with P equals to mass and B equals to 1. So let me show it here. This is just M. Okay. And if you write that, you will get to this equation. This is a general equation that comes from the Reynolds transport theorem. Okay. Which states that the time rate of change of the mass of the system equals to the time rate of the change of the contents of the control volume plus the net rate of the flow of mass through the control surfaces, okay? And then for a steady flow, this is the definition of a steady flow. This term is going to be 0 because for a steady flow, we don't have any temporal variations, right? So we don't have any variations or variability in time. So this term, which represent this term, should be constant. It shouldn't change, and thus the whole integral, the whole derivative of that should be 0. Okay, for unsteady flows, it's not necessarily true, so this is not necessarily 0 for unsteady flows. And then we wrote the continuity equation. This is the continuity equation. This is the conservation of mass law. And so the left-hand side of the equation is 0, and then we are left with this. So this is the continuity equation for a fluid flow in integral form. So this is in integral form. Let me write it down again. So in integral form. And I will briefly touch upon that in the next chapter, that this also has a differential form, that we will use this integral form to get to the differential form of that. And so this means that the net flow rate, and this is just a definition we learned from the Reynolds transport theorem. And this term just represents the net flow rate through the control surface, okay? And so instead of this rho v n, we can define it as rho v bar a, if a is constant. And so you can write it as rho v bar 2 minus a times a2 minus rho v bar 1 times a1. So instead of this term, okay? And then to illustrate this further, I solved one example where we have this kind of pipe flow with air. So we have air here, and the air is flowing through this pipe. And then so the information about section 1, some information about the pressure and temperature is given. And in section 2, the information about the pressure, temperature, and also the average velocity of that section is given. And the question wants us to find the velocity at section 1. Okay? So the way you should do that is you simply write the continuity equation. And because the problem states that this is a steady flow, the first term, which is this term, becomes 0. And so we are only left with this term. And because A1 is equal to A2, we get this relation between the average velocities. And because we don't have the density difference between these two, we only have the pressure and temperature information. So we use the ideal gas law, and using that, you can find that the velocity at section 1 is 219 foot per second, which is kind of smaller than 1000 at section 2. Okay. So in the next lecture, as I said, we will use this Reynolds transport theorem to derive the linear momentum equation. Thank you very much, everyone.